Yes, Aditi, can you just brief what we have discussed yesterday? Aditi, Rakshita W is also left. Yes, Aditi. Yes, what about Manusri? Manusri. Yes, Ashwini. Ashwini.
Yes, sir.
Yeah,
So I was absent for the last class, sir.
you're absent for the last class. Yes, what about Nagaveni?
Sir, even I was absent last class, sir.
You're also absent. Okay. So what about Vadva? Yes, Vadva.
Yes, sir.
Yeah, can you just brief what we have discussed in the previous class?
So yesterday I had some network issues in between, so your voice was not audible and your presentation also was not clear, sir.
Oh, is it so? Then nobody told me.
No, sir, I had some network issues at home.
Uh-huh. Okay. Yes, Girish, can you just brief what we have discussed yesterday?
Sir, I was absent the last class.
You're absent. So yesterday you're absent, huh? Yeah. Yes, Noreen, can you just brief what we have discussed yesterday? Yes, Noreen.
Yeah, so 1 minute I'll tell you.
Yeah. I already shared my PPT. Okay. Okay, let me brief from my side. So we have started discussing about the FM receiver.
The noise in
Yeah, noise in FM receivers, right? So I
we
started with the block diagram of FM.
we discussed band pass filter, limiter,
Yeah,
discriminator. So we discussed the function of each of them and saw a couple of
correct. So we have started discussing about the different blocks of FM receiver model, right? I started with what is the input to the FM receiver model, that is a frequency modulated signal. Then another input is the white noise, right? Then those two will be given as input to the band pass filter. So output of the band pass filter will be what? It will be a frequency modulated signal plus the filtered noise, right? So we denote x of t as the output of the band pass filter, so which is equal to s of t plus n of t, whereas s of t is a frequency modulated signal and n of t is the narrow band noise, right? And we express n of t in terms of in phase and quarter phase components, right? As ni of t cosine of 2 pi of ct minus nq of t sine of cosine of sine of 2 pi of ct, right? Then as I said, the output of that band pass filter will be given as input to the limiter. So the purpose of the limiter is to remove any amplitude variations in the frequency modulated signal, right? as we all know, in case of FM, the amplitude of the frequency modulated signal remains constant. Okay, only the frequency of the frequency modulated signal varies because information resides in the frequency of the FM signal, right? So that will be removed by using a circuit called a clipper, right? So I said by clipping, we will be able to remove the any amplitude variations. Then that limiter circuit will have a bandpass filter, so which is an integral part of that limiter. So that will be suppressing the higher harmonics. With that, what I said, when you do the clipping, we get a square wave, right? We all know the square wave will have harmonics, right? So when we remove those harmonics by a bandpass filter, then we'll be getting a pure sinusoidal signal, and the amplitude of that sinusoidal signal will be independent of the amplitude of the input signal. Okay, then output of that limiter will be given to the discriminator. So what the discriminator will do? So the discriminator circuit will have two components. One is the selective network, right? Or slope network we say, and it is also known as the differentiator. And the second component is what? Envelope detector, right? So the purpose of slope detector, right? What it will do, it will convert the frequency variations into amplitude variations. Then the envelope detector will be able to reproduce the original message signal, right? So output of that discriminator will be given as input to the baseband low pass filter, right? So output of the baseband low pass filter will be the desired demodulated signal. So this is what the block diagram of FM receiver model. And I started discussing about with equations, and we have derived what is the output SNR for this FM receiver and what is the channel signal to noise ratio. And then I think I was with the explaining about the figure of merit, right? If I am correct. So I was there till that point. So just I will go back and I will just run the slides, whatever I have discussed in the previous class, just for the sake of recollection or recall. Okay. So this was my first slide, right, in the yesterday's class. Just now I told about all these blocks, the function and importance of each and every block. Okay, then yeah, I told all about this. Then let me just, yeah, as I said, we can express the narrowband noise in terms of in phase and quadrature phase component, I said, right? So that also is done with mathematical equations. And I said that it can be expressed in terms of envelope and phase also. So with that, this is in terms of in phase and quadrature phase component. So this is in terms of envelope and phase, right? So how do I define R of t is square root of this in phase component and the quadrature component. And this one is the phase. So this one is the envelope and this one is the phase. So phase will be equal to what? Tan inverse of nq of t by ni of t, right? Then, so this is the expression for frequency modulated signal. So just I'm taking this as pi of t, right? So I'm rewriting the FM signal in this form, in a simplified form, right? Then, so I can directly say what is the average power of the frequency modulated signal. So average power of this frequency modulated signal will be AC by root 2 whole square. So which is nothing but A square C by 2. Okay. So that is the average power of this frequency modulated signal. Right. Then, yeah, then I said what is the output of the band pass filter? How do we find this? Then with phasor diagram, I explained this, right? Then, yeah, we found that this is the output of the frequency that is discriminator. Means it will have the message signal and as well as the noise component. So that noise component we are writing like this, right? Then that will be given as input to the baseband low pass filter. No, so with that I was telling about Yeah, all these derivations, I hope it is fine, right? Then we are saying the output of the discriminator means the noise component will be what SND of F can be defined like this, right? So with that, yeah, so this is what I said, that this is the power spectral density of the noise at the what means this is a quadrature component of the power spectral density of the noise which is appearing at the discriminator. Then yeah, so this is we take this as this one, right? So this is the power spectral density of the noise at the discriminator output. Okay, this is at the input of the discriminator, and this will be at the output of the discriminator. Then we pass this through a baseband low pass filter having a bandwidth of plus W and minus W. So this is how we get the output power spectral density of the noise which is appearing at the receiver output. Okay, so these three things are fine, I feel. Then yeah, so here we found what is the output, that is the average power of the output noise. So we found that means we are going to integrate the area, right, of this signal, the third one, right? So this will be what N0 by A square C integral from minus W to W F square into dF. If I do integration and substitute the limits, I will be able to get this as my average power of the output noise. And already I said what is the average power of the demodulated message signal, because the demodulated message signal will be what? That is Kf into M of t, right? So with this, I think, yeah, here it is there. So Kf into M of t is my message signal or demodulated signal which appears to the output of the receiver. So its average power will be K squared into F, right? So this K squared F is the what is the frequency sensitivity, right? So K squared F into P is the average output signal power, okay, which is appearing at the output of the receiver. This by average noise power will give you the output SNR, okay. So that is what is done here. Yeah, see, this is the output SNR expression, right? So as I said, it will be this output SNR will be equal to what? So it is a ratio of the average power of the demodulated signal to the average power of the noise which appears at the output of the receiver, right? So this K squared F into P is the average power of the demodulated message signal. Then in the previous slide I have shown what is the average output noise power. What is the average output noise power? So which is this one, 2N0 WQ by 3A square. So this 3A square will come into the numerator. You all know that, right? Okay. So I hope you people should substitute and see. Yes, this 3A square C into K squared FP divided by 2N0 WQ will be the expression for output SNR. Okay. Okay, so this is one important expression what we need to keep in mind. Then to find the figure of merit, we need to find out the channel signal to noise ratio also. So what is the channel signal to noise ratio? How do we find that? We find the average power of the what? Modulated signal. As I said, modulated signal is what? FM, right? So that is AC into cosine of 2 pi FCT plus pi of t, right? So its average power will be A square C by 2, I said, right? So this is the average power of the modulated signal. Then the average noise power, right, in a message bandwidth, which is equal to N W into N0. So the ratio of these two will give the channel SNR, that is A square C by 2 divided by W N0. So I can write it as A square C by 2W N0 as the channel signal to noise ratio of the FM receiver. So the figure of merit will be what? It is the ratio of output SNR to the channel signal to noise ratio. Means this equation, that is 640, 6.40 divided by 6.41. That will give you the figure of merit for the FM receiver, right? So if I do that, what are the things will get cancelled? See, A square C will get cancelled. Then N naught W will get cancelled, right? So what is left out? The left out terms are written here. So which is equal to 3 into K squared F into P divided by W square. Yes or no? So A square C, W N naught. This A square C will get cancelled, then W N naught. So here W square will be left out, right? Even the 2 will also get cancelled, right? So what is left out here? So 3 into K squared F P divided by W square. So this is the figure of merit. Okay. So figure of merit for the FM receiver is this one. So which is equal to what I said. Oh, sorry. This is the figure of merit, right? So which is equal to what? 3 into K squared F into P divided by W square. So okay. So just to generalize, what we say is the frequency deviation, right? Delta F will be proportional to what? The frequency sensitivity, KF of the modulator. Because right, delta F is equal to right. So we know this already. And even the deviation ratio also we have defined. What is that D? The deviation ratio is equal to what? Frequency deviation, right? Frequency deviation divided by the message bandwidth W. Fine. So what we can say is the deviation ratio D will be proportional to, right? KF means I am taking square root of this. KF into square root of P, right, divided by W. Okay, so you don't have to worry about this. So our goal is to say what is the figure of merit. I think we'll leave it to this point. Okay, why to unnecessarily take these things. Fine. I hope, see, this is an important derivation. 3 things they will ask. So for 8 to 10 marks, they will ask you to find the figure of merit derivation. Yes, is this point is clear? Yes, I am asking you people only. Is this
Yes, sir.
clear till this? Now, we'll consider as an example the sinusoidal message signal and let us try to find out what will be the figure of merit for that. Okay, so as we have done similar to the DSBC and AM. Okay, just here whatever I said about the figure of merit is told here. Means, so looking at this diagram, this equation, what we are observing here, figure of merit, see, there is a quadratic component, right? I will tell about that, what it is. See, the figure of merit of the wideband FM is a quadratic function of the deviation ratio. The deviation ratio is what? Delta F divided by W, right? So delta F divided by W means here W square is there. That is why we say, and even delta F is what? That is proportional to the frequency sensitivity, right? So with respect to that, we say the figure of merit of the wideband FM will be a quadratic function of the deviation ratio. Okay, so in case of wideband FM, the transmission bandwidth, okay, is approximately proportional to what? The deviation ratio. I think this also we have discussed it. Okay, then so when the carrier to noise ratio is high, right? So what happens? There will be an increase in the transmission bandwidth, right? So that will be providing the corresponding quadratic increase in the output SNR, right? In terms, we say when output SNR increases means there will be increase in the figure of merit, right? Because it is directly proportional, right? I hope this point is clear. This is an important point which you need to understand. When the carrier to noise ratio is high, right? So there will be an increase in the transmission bandwidth. Okay, there will be an increase in the transmission bandwidth. that provides the corresponding quadratic increase in the output SNR, or we say the figure of merit. So actually we were discussing about the bandwidth requirement and as well as the performance of the receiver, right? So we started with standard AM. It was requiring twice the highest frequency of the message signal is the bandwidth requirement. Even in power requirement was more in case of standard AM, right? But in DSBC we could eliminate the power requirement, means we could reduce the power requirement, but bandwidth requirement we could not. Okay, it is same as that of the standard AM. But in SSB we could achieve both, means we could reduce the bandwidth requirement and as well as the power requirement. Fine. So, but so as next level, the FM, people thought that okay, it requires less bandwidth and as well as less power, but it is not so. So it requires more bandwidth, but with that, what we can say is the performance of the receiver is much more superior than the other AM receivers. So this is what the meaning of this. Okay. So as the carrier to noise ratio increases, I say transmission bandwidth will increase. So with that, we say there will be a quadratic increase in the output SNR or figure of merit. Right. So that is what the last line which I have written is. This frequency modulation provides the useful mechanism for the exchange of increased transmission bandwidth for the improved noise performance. Okay, because the figure of merit will be more than one. Yes, is this fine? So this is these two sentences are very, very important. Okay, though the transmission bandwidth required for FM modulation is more, so with that it is providing an improvement in the noise performance of the receiver. Okay, so let us now consider the example of singleton modulation. Okay, so I am considering a sinusoidal signal, right, having a frequency FM. Okay, this is the frequency of the modulating signal, and see, I can express the frequency modulated signal as like this, right? S of t is equal to AC cosine of 2 pi FCT. See, we know this one, delta F by FM will be what? Beta. That is the modulation index, right? So this into sine of 2 pi FMT, right? So this is other way of expressing the frequency modulated signal, right? So AC cosine of 2 pi FCT plus delta F by FM is nothing but beta into sine of 2 pi FMT, right? So we can write means the second portion, okay, the second portion of this equation, that is so usually we used to write AC cosine of 2 pi FCT plus this term, 2 pi k of integral 0 to t m of tau into d tau, right? So now I am equating the second term to this one. Okay, so 2 pi k of integral 0 to t m of tau into d tau is nothing but delta F by FM into sine 2 pi FMT. If I differentiate this equation, okay, with respect to time, and if I solve for m of t, then what I get? So 2 pi k of m of t at this point, here delta F by FM into derivative of this sine of 2 pi FMT. So derivative of sine is what? It is cosine, right? So cosine 2 pi FMT into 2 pi FM will get. So if you do the simplification, means 2 pi will get cancelled, and that FM will also get cancelled. I can write what is m of t. So m of t will be equal to delta F by kf into cosine of 2 pi FMT. Yes, is this you are getting? You need to do one step here. If I differentiate this, okay, with respect to time, so what you will get as a first part, I will be getting 2 pi kf m of t. Is this clear? As the LHS, then RHS, what I get? Delta F by FM into, see, derivative of sine of 2 pi FMT will be what? Cos of 2 pi FMT into 2 pi FM, right? So that 2 pi will get cancelled. Even FM will also get cancelled. If I can write as m of t will be equal to delta F divided by kf. So this kf was there this side, right? LHS side. So delta F by kf into cosine of 2 pi FMT. Yes, is this fine? Yes, is this fine? Could you understand this? How do I get
Yes,
this
sir.
one? Hmm?
Yes, yes, sir.
Differentiate and then cancel. So now I can find out what is the average power of this message signal. So this is my message signal, right? So average power of the message signal. How do I find this? See delta f by kf, that square, right, into cosine of 2 by fmt. I can write it as what magnitude is 1, right? So that is 1 by root 2 whole square. It is nothing but 1 by 2. So I can write as what? Delta f whole square divided by 2 into k squared f as the average power. Okay, see the average power of this message signal, delta f by kf whole squared into 1 by root 2 whole square, right? So it is nothing but this one. Okay, so this is the average power of the message signal. So now I can substitute this value of p in the expression of figure of merit, what we have done in the previous slide. I think here now. Yeah, so if you substitute the value of p as that, then see what we can write. Okay, so which is done in the next slide. So I am substituting the value of that p in the output SNR expression. Nothing wrong. Okay, so 3 because we know what is the expression for output SNR, right? So it was p was there. So I'm just substituting the value of p as this one. What is that? Delta f whole square divided by 2 into k squared f. Yes, just write the expression for output SNR was here, right? Yeah. So in this equation, I am substituting the value of p as what? Delta f whole square divided by 2 into k squared f. Okay. So if you substitute that, I think you will be able to. Yes, I hope you noted that expression, output SNR. So please do that. I think if you don't do it, then it will be just, yeah, please have a note of this equation. What is the expression for output SNR? You substitute the value of P as what? Delta F whole square divided by 2 into K squared F. And even you can note down the expression for channel signal to noise ratio also. Let us see what we can write for figure of merit for a sinusoidal modulating signal. I hope noted. Yes, I will ask the students. If you don't answer, then I will not give attendance, okay? Because you just like that, you cannot say I don't know. That's why I'm insisting you people to note down few things. Hope noted. Shall I go to the next slide?
One second, sir.
Oh. Good, at least like this, I expect some response from your end.
Done, sir.
Done. Thank you, ma'am. Okay. So I hope this also noted, na? The figure of merit. You have a note of this also, so it will be useful. This is the figure of merit for FM, right? Because many people still they are not aware what is figure of merit. So it is a ratio of output SNR to channel SNR. So this output SNR we measure at the output of the receiver, and this is channel SNR we measure at the input of the receiver. Okay. And then okay. So I was telling with respect to Singleton modulating signal, right? Then I wrote the expression for FM signal, right? So some part I have written for my convenience in this form. Then I do the differentiation and I derive what is M of t. Then I am finding what is the average power of that message signal. See, the purpose of writing in this form is to find the expression for M of t and then to find the average power of that message signal. That is why I have written the frequency modulated signal in this form. Okay. So now if we substitute the value of T in the output SNR as that. So you'll be getting the expression as like this. Okay. Then we know what to substitute for beta. So beta is nothing but what delta F by FM, right? So here FM will be is nothing but W. Okay, that is a message bandwidth, right? So if I substitute beta in place of delta F by W, so here delta F square is there and W square, right? I can write it as a beta square. That is why it is written 3 into A square C beta square divided by 4 N naught into W. So 1 W I need to keep away, right? To write that as a delta F by W whole square, which is nothing but beta, right? That is beta square. Fine. So this is the expression for output SNR. Then I am just substituting and finding what is the figure of merit for that, right? So output SNR by channel signal to noise ratio is the figure of merit. So this divided by, what is the expression for channel signal to noise ratio? It is A square C divided by 2 N naught W, if I am correct. Am I correct? I said the channel signal to noise ratio will be what? A square C divided by 2 N naught W or 2 W N naught. Say yes or no. That is why I told you people to note down. Channel signal to noise ratio of this FM receiver. Is it A square C divided by 2 W N naught?
Yes, sir.
So if I take the ratio of this output SNR and the channel signal to noise ratio, I think what will get cancelled? A square C, then this 2 N naught W will get cancelled, right? So what will be left out? 3 by 2, right? 3 by 2, then delta F divided by W whole square is left out. So this delta F divided by W is nothing but beta, right? So I can write it as 3 by 2 into beta square. So this is the figure of merit, okay, for FM receiver when the message signal or modulating signal is a sinusoidal signal. Okay, so it will be what? 3 by 2 means what? It is 1.5, right? So 1.5 times the beta square. Okay, beta is the modulation index, right? So compared to either DSB-SC or AM receivers, so the figure of merit for FM receiver is higher than 1, right? In that way, we say the performance of the FM receiver in the noise is superior compared to any other receivers. Oh, is this clear? So as I was telling, this beta is delta F by W, right? So this W is the what bandwidth of the low pass filter, which we use at the output side, right? That is a post detection low pass filter we call. That is a baseband low pass filter. Okay. Fine. Yes, is this point is clear? So figure of merit, we found that it will be 1.5 times beta square, right? So to do further, okay. So yeah, here what I wanted to say is this W is the bandwidth of the low pass filter, and we are saying it is not related to the sinusoidal message signal FM, right? And so usually we choose that band pass filter bandwidth to pass the desired message signal, right? In that way, we say we can equate W is equal to FM. Okay, right? That is what is written here. See, for specified system band W, the sinusoidal message frequency FM may lie anywhere between 0 to W. So we can consider W equal to FM as. Okay, so yeah. This is the figure of merit for the AM receiver, right? We found that it is 1 by 3, right? So now to have a comparison of that and means the figure of merit of the AM receiver and the figure of merit of the FM receiver. So we say this 3 by 2 beta square will be greater than 1 by 3. We all know that, right? So I can write the expression for beta. So what I can write beta as square root of 2 by 3, right? So beta will be greater than square root of 2 by 3. I hope you understand now. It is beta square. So 2 by 3 into 3, it will be 9, or I can write as 3 square, right? So beta square will be greater than 2 by 3 square, or I can write beta will be greater than square root of 2 by 3. So which is nothing but 0.47. So this value of beta, okay, will be defining the transition between this narrowband FM and the wideband FM, right? But we say even beta less than 1 is narrowband FM, beta greater than 1 is the wideband FM, we say. Yes, up to this point, is this clear? Okay. Okay, so this is all about the FM receiver. Okay, finding the expression for figure of merit. Okay, and we found that the figure of merit for the FM receiver will be, the general expression is that k squared f into p divided by w, right? Yeah, k squared, that is 3 times k squared f into p divided by w square is the expression for figure of merit. If we consider a sinusoidal message signal, then we could prove that it will be 3 by 2 into beta square, right? So it is 1.5 times the beta square. Yeah, so similar to, we have discussed even threshold effect in AM receiver also, right? So similar to that, here also we'll see what is the capture effect, and one more is threshold effect. Both the things are there. So to understand what the capture effect is, what I wanted to say is this FM system, okay, have the inherent ability to minimize the effects of unwanted signals, right? Unwanted signal is nothing but a noise, right? And even the same thing can also be applied to the interference signal also. So this is what we discuss is means the FM system have the ability to minimize the effect of noise, right? Same thing can also be applied to the reduction of the interference. So we all know what is interference and what is noise. So the difference, right? So interference is something which is produced by another FM signal, right, whose frequency content is very near to or close to the carrier frequency of the desired FM signal. Means if I am generating an FM signal of frequency, say 1 megahertz, if I have another FM signal which is also generated, it is using a carrier frequency near to this, the first one. Okay, so then there will be an interference, right? So how do we, what about the reduction of interference, right? So the interference suppression in the FM receiver also works very well, okay? So only when the interference is weaker than the desired FM input. So this is the important thing. Okay, when the interference is weaker than the desired FM signal, it will be the same as that of the noise effect. Okay, but when the interference is stronger, okay, when the interference is stronger than the desired FM signal, then what happens? The receiver will lock onto the stronger signal. Okay, then with that, so we will be able to suppress the desired FM input, right? So that is a serious concern what we need to think, right? When the interference is weaker, absolutely there will be no problem. Okay, so it is possible to suppress that interference by using the same thing, right? When the interference is strong, what happens? The receiver will track or lock to the stronger signal. So with that, we are going to suppress the desired FM, but we are going to hear only the unwanted or undesired FM signal, right? So this is the second case. So when it is weak, yes, we will be able to suppress the interference. When it is stronger, we will not be able to do anything. When it is equal, okay, when they are of nearly equal strength, then what happens? The receiver will fluctuate back and forth between them. I hope you understand this point. When the interference means the desired FM signal and the one which is near to the another desired FM signal, right? Means one is the desired FM signal, another one is the undesired one. Why that is undesired? So we are interested in a FM signal which is broadcasted at 1 megahertz. But I have another FM signal which is broadcasted at 1.1 megahertz, right? That 1.1 megahertz FM signal will be interfering with the 1 megahertz signal, right? So if their strength, if they are having an equal strength, then what happens? The receiver will be fluctuates back and forth between those two signals. So that phenomena is known as the capture effect, we say. And this is one of the distinct feature or characteristics of the effect, capture effect. I hope it is clear what is capture effect. I said this FM system have the ability to minimize the effect of noise, right? The same thing can also be applied to the interference which is produced by another FM signal, right? Whose frequency is close to the carrier frequency of the desired FM signal. So here three cases we consider. One is when the interference is weaker than the desired FM signal, then the interference will be suppressed by the FM receiver. Okay. The second case is when the interference is stronger than the desired one, then what happens? The receiver will lock onto the stronger signal. Okay. With that, it will be suppressing the desired FM signal. So that is a serious issue, right? Then the third case is if the desired signal, desired FM signal, and the undesired one, means that is the interference signal, right, have the same signal strength. Okay, if their strength is same, then what happens? The receiver will fluctuate back and forth between those signals. That phenomena is known as the capture effect, we say. Okay, this is not there in case of any other receivers. I hope understood the capture effect, the meaning of capture effect. Yes?
Yes, sir.
No. Okay, next one is the threshold effect. So similar to the this also we have discussed in AM receivers, na? What is threshold effect and all. So this all related to the value of output SNR and the carrier to noise ratio, right? When the carrier to noise ratio is large, only those equations of output SNR will be valid. So we know what is the expression for output SNR, right? So I repeated here. So which is equal to 3 into A square C, K square F into P divided by 2 NR WQ, right? This is the expression for output SNR of the FM receiver, and this equation is valid only if the carrier to noise ratio, right, is high compared with the unity. Okay, so this equation is valid only when the carrier to noise ratio is high compared with the unity, right? And it is found experimentally that the input noise power, okay, input noise power is increased so that the carrier to noise ratio will be decreased. Carrier to noise ratio. Okay, then the FM receiver will break. We say the FM receiver breaks. Okay, means as the input noise power is increased, the carrier to noise ratio is going to decrease because carrier power to the noise power. When the noise power is increasing, right? So the carrier power will be decreasing, isn't it? So we say the carrier to noise ratio will be decreased. With that, we say the FM receiver will be break. Means the breaking means what? It won't work properly, right? Means we will be able to hear only the noise rather than the desired music or station information, right? So to understand this further, so we will be able to hear first the individual clicks. So try to understand this. What is the click and all I will tell. At first, the individual clicks will be heard in the receiver output. Means you might have experienced that some noisy kind of sound. Okay. So, and as the carrier to noise ratio decreases, so there will be further increase in the clicks. Okay. So these clicks will be rapidly merged into the crackling sound or sputtering sound, we say. Okay. At the first, what I said, individual clicks will be heard in the receiver output. and as the carrier to noise ratio decreases, what happens? The clicks will be rapidly merging into crackling or sputtering sound. Okay, so I said that when the carrier to noise ratio decreases, what happens? The FM receiver will break, right? So near the breaking point, this is important, near the breaking point, this output expression for SNR will be failing. That fails. It cannot be like this. Okay. By predicting the value of the output SNR larger than the actual ones. Okay. This is known as the threshold effect. I repeat once again, I said that the output SNR expression of the FM is valid only if the carrier to noise ratio is high compared to unity. Okay, but experimentally it is found that as the input noise power is increasing, the carrier to noise ratio will be decreasing. So with that, we say the FM receiver will break, means it won't perform properly, right? First, we will be hearing the individual clicks at the receiver output, and as the carrier to noise ratio decreases further, we will be hearing further clicks. Okay, that clicks will merge into crackling or sputtering sound, we say. You might have experienced this whenever you are listening this FM. Okay, so near that breaking point, the expression of this output SNR will be failing. Okay, by predicting the value of output SNR larger than the actual ones. So that phenomena is known as the threshold effect, we say. Okay, so definitely they will ask definition in the exam. Define threshold effect, capture effect, like that. Okay, so try to understand this. Okay, further understanding about this, let us have a discussion. Means the qualitative discussion of this FM threshold effect. Okay, by considering further analysis. Okay, so here what I was telling is the threshold effect, na? So threshold effect, right? So here the threshold will be defined as the minimum carrier to noise ratio that yields an FM improvement. Okay, so that is not significantly deteriorated from the value predicted by the usual signal to noise equation, assuming the small noise power. Oh, clear? So threshold is about the minimum carrier to noise ratio. Right? With that, there will be an improvement in the FM reception. Right? Means its value will not be deteriorated. We will be able to hear a nice station program. Okay, without any noise. Hope able to catch this point. What is the minimum carrier to noise ratio? The minimum carrier to noise ratio is the value of threshold. Let us see how much it is and all. Okay, how many dBs we can say this is the minimum value of carrier to noise ratio should be there to hear the or to perform the FM receiver properly. So to have a qualitative discussion of this FM threshold effect, so let us consider first there is no signal present. Means I am not having any signal. Okay, so with that, what I can say, the carrier signal will be unmodulated, isn't it? So when there is no message signal, then I will be getting the unmodulated carrier. Okay. So I can express that composite signal. What I can say, when there is no signal component, right? Only I will be having a unmodulated carrier. So how do I express that composite signal at the frequency discriminator input? Okay, so that is shown here. Yeah, see, I can express that composite signal, that is output of the band pass filter. Na? So that will be an input to the frequency discriminator, right? So it is only an unmodulated carrier along with the noise, right? So I can write AC plus Ni of t cosine of 2 pi f ct minus NQ of t into sine of 2 pi f ct. So this is the expression what I can say. So this is it, the input of the frequency discriminator. At this point, this equation you could get, except there is no message signal, means I will be having only the unmodulated carrier, means that is AC cosine of 2 pi f ct is one component. Then the next is the noise. So one step I have skipped here. Means what you can write is x of t is equal to AC cos of 2 pi of ct plus n of t. What is n of t? I can write n of t as what? N of t cosine of 2 pi of ct minus nq of t sine of 2 pi of ct. Then if you take cosine term common, then we can take this AC plus Ni of t as common. Then I can write it as AC plus Ni of t into cosine of 2 pi of ct. Right? Yes, I hope you understood. X of t is the what? Output of the bandpass filter, right? Means that is nothing but an input to the discriminator. So as I said, I don't have any signal. Means I don't have a message signal. With that only, what I said, that I will be getting only the unmodulated carrier. So unmodulated carrier is nothing but AC cosine of 2 pi of ct plus n of t. So I used to write n of t as Ni of t cosine of 2 pi of ct minus nq of t sine of 2 pi of ct. So in the first two terms, that is AC cosine of 2 pi of ct plus Ni of t cosine of 2 pi of ct, I can take AC and means cos 2 pi of ct, I can take it common, right? So with that I can write AC plus Ni of t into cos of 2 pi of ct minus nq of t into sine of 2 pi of ct. Yes, is this equation fine? Hello, my dear students, should say, is this clear? I said x of t will be carrier component plus the noise. Okay, carrier is what? AC cosine of 2 pi of ct. Then noise is n of t. So I used to express n of t as what? This in phase and quadrature component. Hope could you get this point? Yes, I'm not hearing any response.
Yes, sir.
Yeah. Okay. Yes, Gautam Hegde. Gautam Hegde.
Yes, sir.
Could you understand this point, man? How I wrote x of t as this equation? Can you just repeat from your side? Gautam Hegde.
Yes, sir.
Can you just say how I got this equation? X of t. They said we used to write x of t as s of t plus n of t, right? But then x of t we used to write as s of t plus n of t.
Yes, sir.
So here what is s of t? S of t will be only the unmodulated carrier. Okay. Means I can write that s of t as AC cosine of 2 pi of ct. Okay. Then plus n of t is what? Ni of t cosine of 2 pi of ct minus nq of t sine of 2 pi of ct. I said in the first two terms, I can take cos of 2 pi of ct as common. So what is left out? AC plus Ni of t into cosine of 2 pi of ct minus nq of t into sine of 2 pi of ct is the expression what I get. Okay, so let me draw the phasor diagram for this equation. Okay, so already we know, right? This is AC. So with the reference, right? This is the AC point. Then Ni of t. So this point is Ni of t from here to here. Ni of t, right? And this will be what? Envelope R of t. And this is the quadrature component NQ of t, right? So I take this angle as psi of t and this angle as theta of t. Okay, this angle as theta of t. And this will be my x of t. Okay, this expression. Okay, so I denoted here 2 points. One is P1. So I made 2 points. One is P1. So it is very interesting and you should focus here. So 2 things are there. I told how to draw the phasor diagram of this. So I hope by this time you know how to draw it. Okay. So this is the quadrature component. This is the in-phase component. This is my carrier AC. Okay. This is my R of t. That is the envelope, right? And this is the x of t for this envelope. With this equation. Okay. So here this Ni of t and Nq of t, already said these are the in-phase and quadrature components of the narrowband noise, right? Yeah. So this phasor diagram gives the phase relations between the various components of this x of t, right? So here the amplitudes and phases of ni of t and nq of t will change in time in a random manner. Please take this point: amplitudes, okay, and phases of this in phase component ni of t and the potential component will change with time in a random manner. Amplitude and phase of this ni of t and nq of t will change with the time in a random manner, right? So with that, I have a point P1, I was telling, right? Point P1, another point I have P2. Okay, so what is this point P1? So it is the tip of the phasor representing x of t. Point P1 is the tip of the phasor representing x of t, right? And another point P2. Okay, what is this one? P2 is the tip of the phasor representing the carrier. So this is my carrier, right? So this is origin. From here to I return on arrow road. This is my carrier AC component. Okay, there is a carrier AC, and this one is the in phase component, then potential component R of t and x of t we know. So as I said, the amplitude and phases of this in phase and potential component change with time in a random manner. So as the amplitude and phase of this in phase and potential component changes randomly with time, what happens? The point P1, okay, the point P1 will be wandering, okay, around the point P2. Means whenever the amplitude of this in phase and quadrature phase component changes, no, so the point P1 will also become equal to point P2. Okay, in that sense, right? So the point P1 wanders around the point P2. I'm saying here, the point P1 is this one, right? That is the tip of the phasor representing x of t, and P2 is the what? Tip of the phasor representing the carrier. So whenever the amplitude and changes, amplitude and phase of the in phase and quadrature component changes with the time randomly, the point P1, okay, wanders around the point P2. Hope you understand this. When the amplitude changes, means amplitude decreases, so point P1 will be nearer to the point P2 in that way. Okay, so that happens when the carrier to noise ratio is large. Okay, when the carrier to noise ratio is large, during that time, the in phase component and potential component are usually smaller than the carrier amplitude. Okay, when the carrier to noise ratio is large, when the carrier to noise ratio is large, means carrier component is larger than the noise component. In that way, the in phase component, that is ni of t and nq of t, will be small, right, compared to the amplitude of the carrier signal. Means the point P1 will be nearer to the point P2, what I wanted to say. Okay, so wandering point P1 spends most of its time nearer to the point P2, right? So in that case, the angle theta of t will be approximately equal to what I can write, nq of t by AC. Okay, nq of t by AC is the angle theta of t. So this is important. Okay, so within multiple of 2 pi. Hope this point is clear. When the carrier to noise ratio is large, what happens? The carrier amplitude is much greater than the in phase and quadrature component of the noise. So with that, what we can say is the point P1 will be wandering nearer to the point P2. So with that, what we can say, the angle theta of t will be equal to nq of t by AC, we say, right? So that is the first case. The second case is when the carrier to noise ratio is small. Okay, when the carrier to noise ratio is low or small, what happens now? The point P1, okay, the wandering point P1 occasionally sweeps around the original, okay, around the origin, and theta of t will be increasing or decreasing by 2 pi radians. So whenever the carrier to noise ratio is small, the point P1, okay, will sweep around the origin. Means this is the origin, right? This is the point. O is the origin, right? And the value of theta, either it can increase or decrease by what? 2 pi radians. I hope you should be able to visualize this. I said the two cases. One is when the carrier to noise ratio is large, what happens? When the carrier to noise ratio is small, what happens? Okay. So when the carrier to noise ratio is large, what is happening? The in phase and potential components will be much smaller than the carrier. In that case, what I can say is the angle theta of t will be approximately equal to NQ of t by AC. Okay. When the carrier to noise ratio is small, in that case, the point P1, that is tip of the X of t, will be wandering or sweeps around the origin, and the value of theta of t, either it can increase or decrease by the value of 2 pi radians. Okay, so you can consider a circle and then it will be rotating, okay, in that direction. Means it will oscillate between the value, either it can increase or decrease by 2 pi radians, I said, right? So I will come back to this, what is happening here. I think we would like to understand about clicks now. So this is all about that clicks. I think when we were discussing about threshold effect, I was telling about clicks, right? At first we receive click, individual click, and then as the carrier to noise ratio increases, that the click sound will become sputtered noise. So this is the output of the, this is at the input of the discriminator, theta of t. Okay, this is at the input of the discriminator, and theta dash of t is the output of the discriminator. Means it is a derivative of theta of t, right? So this all we know. So these are the what is that the impulse components, impulse like components in theta dash of t means this is one impulse function. I hope you understand this, right? This is one impulse function. Yes, you should also ask. See, this is a one impulse function. Yeah. So theta dash of t, what I said, it is the output of the frequency discriminator. So it will be derivative of theta of t. So theta of t is the input to the frequency discriminator, right? So as I was telling about, yes, the means when the carrier to noise ratio is small, I said this theta of t will be either increasing or decreasing by 2 pi radians. So this point is increasing by 2 pi radians. Then again constant. Again there will be further increase, right? So you consider this one point. Then another point. This one is also here increased by 2 pi radians from 2 pi to 4 pi, right? So 2 pi radians is increasing. Then another thing here it is decreased by 2 pi radians. So three cases we have considered, right? As I said, when the carrier to noise ratio is small, right? Theta of t will either it will increase or decrease by 2 pi radians. So two cases I have considered for increasing 2 pi, and one case I have considered for decreasing 2 pi radians. So whenever this there is an increase in this theta of t, no? So the derivative of that, what I am getting the impulses, right? So here increasing one impulse, first one, next another impulse, right? Then for this one I am getting negative impulse. Okay. Just I would like to throw some light on this. What I mean by that? See, that is the figure 611. Na? Yeah, this is a figure 611. This will be illustrating about that clicks. Okay. So it shows how, in a rough way, right? Excursions in theta of t. Excursions in theta of t will produce the impulse-like components, that is theta dash of t, which is equal to what? D by dt of theta of t, right? So the discriminator output, what I used to say is a V of t, no? Which is equal to theta dash of t by 2 pi, means 1 by 2 pi into d by dt of theta of t. It is nothing but that one only. Okay. So these impulse-like components have the different heights, right? Depending upon how close the wandering point P1 comes to the origin, right? So if it is, so as I said, it is will be varying by plus or minus 2 pi radians. Okay. So that is the first figure what I have shown. So what we observed in the second figure is, so whenever the signal, okay, when the signal is passed through that low pass filter, this one, right? So we get a impulse like components, so which are excited in the receiver output, which are heard like a clicks. Okay, so these clicks will be produced only when this theta of t changes by this plus or minus 2 pi radians. Hope understood this point. Respect to the previous figure, what I was telling here, I think, yeah. So with respect to this phasor diagram, I said two cases, right? When carrier to noise ratio is large, what happens? When carrier to noise ratio is small, what happens? When carrier to noise ratio is large, during that time, the value of theta of t will be what? NQ of t by AC, because carrier component is much greater than the noise component, right? And when the second case is when carrier to noise ratio is low, what happens? This point P1 will be around the origin. Okay, it will sweep around the origin, means it can increase or decrease by 2 pi radians. So with that, what I wanted to express here is, so this is what the picture I have shown, how the value of theta of t is varying, right? At this point it is varying by 2 pi radians, then next 2 pi radians, then it will decrease by 2 pi radians. So this is at the input of the discriminator. So output of the discriminator is what? The derivative of this. So I get the impulses, right? So these are the impulses which I get, means these are the clicks what I will be able to hear at the receiver output. In a simple words, what I wanted to say. Okay. Hope you understood this point. Yeah, it is a little bit tricky, but I made my effort to explain in as simple as way. Yes, I hope you got this point. See, first of all, you should get this thing, means the phasor diagram and this equation, how I got this, right? How do we write this phasor diagram? Then I said the amplitude and phase of this noise component, that is in phase and quadrature, vary with the time randomly, right? So whenever it is varying randomly with the time, for two cases I consider, when it is large, what happens? When it is small, what happens? So with respect to that, how the clicks will be generated at the receiver output, I am telling. Okay. So it is simple, try to understand. Okay. And many times the question will be asked on this. We know people will not give attention and they will not read also. That is why it is very simple thing. Okay. Fine. So now let us try to understand the conditions. Let us try to find out the conditions required for that clicks to occur. Okay. Right. I was telling at the receiver output, you will be able to hear the clicks, right? So when the clicks will occur, already we know that when the clicks will occur, just we are reiterating on that. So what is that condition? We say the positive going clicks. Okay, the positive going clicks will be occurring whenever this envelope R of t and the phase psi of t, okay, of the narrowband noise satisfy these conditions. Means the first thing is what? R of t is the envelope of the narrowband noise, right? That should be greater than the carrier component. Okay, then this is the envelope. And second thing is phase. This phase should be less than pi. Okay, so which is less than pi of t plus this is the change in phase with time. Okay, in a nutshell, what I can say, the derivative of that phase, noise phase, should be greater than 0. Then I will be able to hear the positive going clicks. Okay. Right. So that one only is reiterating here. I said the phase theta of t is the what? Resultant of the phasor x of t that will change by 2 pi radians in the time increment dt. Right. So during that time, the phase of the narrowband noise will increase by the incremental amount d into psi of t. Right. So similarly, we can find out what is the condition for negative going clicks. Okay. So positive going click, what I said, d by dt psi of t should be greater than 0. So three conditions, three equations you need to write. One is R of t, that is the envelope of the noise component should be greater than the carrier component. Then second thing is the noise phase should be less than pi, and that should be less than noise phase plus incremental change in the phase of the noise. Then the third one is d by dt of psi of t should be greater than 0. Okay. This is for positive going clicks. For negative going clicks, the conditions are, so one is,
Sir,
oh,
sir 12-5 ಆಯ್ತು.
sorry madam, sorry. I will stop madam.
Okay, sir. Okay.